Alright, we're just going to continue what we were working on just a second ago. This is the example that got cut off when time ran out. We were looking at Cu2SO4 and we were going to name this fellow. And after we name this, we'll proceed to look at how to write chemical formulas for these, and it's really not that complicated. First, we'll treat this just like we did the others and name the first ion. It's copper. Something I should notice about copper, it's a transition metal. It's not a member of group 1, 2, or 3. And also, it's not one of the exceptions. It's not zinc, cadmium, or silver, so that means I'm going to need to put a Roman numeral in parentheses for it. Again, just to remind ourselves, the Roman numeral should be the same as the charge, and I have to find the charge. How am I going to do that? I'm going to use my good old deductive reasoning. I know that compounds have to be neutral, and I know that the charge of sulfate is -2. That means that the collective charge of copper must be +2. And so if there's a +2 charge for 2 coppers, that means each copper must be +1. So this is copper 1, and the name of the second ion is sulfate. And so again, we've just illustrated how simple this can be with a little deductive reasoning and knowing the names of my polyatomics. The next thing we want to do is write formulas for these non-binary compounds. The good news is it's not much different than writing it for binary compounds. There's 2 steps. We still write the formulas and symbols of each ion. So in this case it can be an element or it might be a polyatomic, but we're going to need its symbol including its charge. And we're going to balance the charges again by supplying subscripts. If I need a subscript for a polyatomic ion, here's a new part. I've got to put it in parentheses. Saying that I need NO3 2 is not the same as saying I need NO32. That doesn't make sense. So since those polyatomic ions are self-contained units, if I need more than one, I will contain them in parentheses and indicate that on the outside. A good example of this is aluminum nitrate. We're going to tell that we're going to have a polyatomic ion present because nitrate does not end in "ide." There are 2 polyatomics that end in "ide," hydroxide and cyanide, so just be aware of that. But for the most part, if I do not end in "ide," I am not binary. So I know there's a polyatomic present, and so I'm going to write the formulas and symbol for each ion. Aluminum is +3 Al because it is in group 3. Nitrate is NO3 and it carries a -1 charge. I would know that from right now from looking at my list of polyatomics. I would know that in 2 weeks from looking in my brain where I had memorized that. Okay, so we're going to play the same game we played earlier. The least common multiple here is 3. So I need 1 aluminum, and in order to get enough nitrates to go with that, I'm going to have 3 of them. Each nitrate will take in 1 electron. Aluminum wants to give up 3. So when I write this formula, I'm going to have aluminum, and I'm going to have the nitrate ion inclusive 3 times. Again, having this whole unit 3 times is much different than having NO33. So be sure that you are putting them in parentheses to indicate that. This would be very much like having Cl-. It's just we have NO3 now that carries the charge. Lead-4 acetate, another example. We're still going to write the formula and symbol for each ion. This is a transition metal. I recognize that because I have a number in parentheses. Actually, lead is not a transition metal. Lead and tin are outside of that series. They're in group 4. But if you remember, we skipped over group 4 because it was kind of strange. Well, we just treat them like transition metals. So in this case, they've supplied me with the charge. That means Pb for lead, and it's +4 because of the Roman numeral there. And then acetate, I will look up or memorize, which is C2H3O2 -1. So now we're going to do the old balance the charges, and away we go. Lead is +4, acetate is -1. That means the least common multiple is 4. So I have a charge of 4 already on the lead, but I'm going to have 4 acetates in order to get there. And again, we put that 4 outside of the parentheses that are encasing the acetate so that we know we need 4 of the acetate unit inclusive. Another example, calcium phosphate. Again, we're going to write the formulas and symbols for each. Calcium is +2 because it's in group 2. Phosphate is PO4 -3 because it is. And again, we got a least common multiple in this case of 6. To get to a charge of 6 for calcium, it's going to require 3 of them. To get to a charge of 6 for phosphate, it's going to require 2. And so Ca3, PO4 taken twice, PO4 in parentheses, 2, is my formula. We can also arrive at this by swapping charges like I showed you in class. If you remember, you can take the charge from one, bring it over, take the charge from the phosphate, bring it over, and away we go. That concludes what we want to do in this talk as far as ionics. Now there is another category of compounds that we wanted to talk about today that's part of Objective 1. Objective 1 talks about naming and writing formulas for ionic compounds and naming and writing formulas for simple molecular compounds. Simple molecular compounds fall under the heading of binary molecular. Again, binary means only 2 types of elements, and in this case the molecular part means that we have covalent bonding. When we have covalent bonding, that almost always means we have nonmetals. It's not 100% true all of the time, but it's generally a good rule of thumb to assume that if we're covalent, we're all nonmetals. And so essentially this means that if I see a binary molecular compound, it will have 2 elements that are not metals being bound together. To do the names and formulas for these, we have to know some Greek prefixes. Because these guys are sharing electrons instead of transferring them, they open up the door to many more possibilities. Like with copper oxide earlier, we had 2 possibilities. When we go to bond nitrogen and oxygen, we have many possibilities. And so we need a way to differentiate these, and we can't use charges because they don't have charges. They're sharing electrons, not giving and taking them. So the prefixes we'll use are good old tried and true Greek prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. We could go beyond this if we wanted, but this will suffice for what we want to do. And so the first thing we're going to do is realize that the first nonmetal will only get a prefix if it has more than one. If there's only one, we're not going to do it. So if I have something that is like CO2, for example, we don't call that monocarbon dioxide. You've never heard of that. You have heard of carbon dioxide. So we just leave that prefix off unless there's more than one. For the second element, we always give it a prefix no matter what. If there's 1, 2, 3, 4, or 50, we give it a prefix. And we always change the ending to "ide." All binary compounds always end in "ide." So that's just how we handle that. So we looked at this example a second ago, CO2. So we named the first element. There's only one of them, so I don't need a prefix. That's carbon. And if I look at the second element, that's oxygen. There are 2, so it's di. And then we add "ide" to the ending, so 2 oxygens becomes dioxide. Another example, CO, similar compound, not the same. We're still looking at it as a singular carbon, so there's no prefix for the carbon. But now there's only 1 oxygen, and so to show that, I use the prefix mono, obey a little English rules, and call it monoxide. Notice I did not put monooxide. That looks funny. We tend to ignore double vowels like that when we see them. Especially with the O, because English wants to pronounce that as oo, and so we tend to drop that off. Next example, N2O4. This time the nitrogen does not have just 1, there's 2, so the first element will get a prefix. So this is going to be 2 nitrogens, or dinitrogen, and then we have 4 oxygens, so we use tetra, and then we translate the ending to "ide" again, so tetraoxide. Dinitrogen tetraoxide. Last example for this type of system, CCl4. Again, that's a singular carbon, so we don't need a prefix for that. But we do have 4 chlorides, so we're going to use our tetra prefix for our chlorides. So we have carbon tetrachloride. AlCl3. What do you want to do with this? This is a metal and a nonmetal. Keep your periodic table in front of you until you get used to it and recognize the metals, because you don't want to say aluminum trichloride. I see people say this all the time, but metals and nonmetals are not named that way. We don't use prefixes with metal, nonmetal. So when we start mixing these together, be real careful. Make sure there's no metals present, or that it's both nonmetals, however you want to look at it. Don't fall in the trap. If I have the names of two binary molecular compounds, how can I write the formulas for them? So we've talked about how to name them. How do we go the other way? Well, it's really easy, actually. All we do to write the formulas is not worry about charges, number one, because they don't have any. They're all nonmetals, so they're ionic. What we're going to do is just translate those prefixes back into subscripts, and it'll be super easy. So silicon dioxide, looking at that, silicon is Si, and there's no prefix there, so that must mean I only have one of them. If I look at the oxide, that comes from oxygen, so that's O, and the di tells me there is 2, and so that becomes SiO2. Another example, diphosphorus pentachloride. Phosphorus is P, and the di tells me there are 2. If I look at the chloride, that's Cl, and there are penta of them, or 5. And so we just translate that back to a subscript, so P2Cl5. Nitrogen monoxide, following the same reasoning. Nitrogen has no prefix, and so that means there must only be one. Mono means one for oxygen, and so nitrogen monoxide is NO. That is really, really simple. This is the one that you should do the best on. It's not complicated. Don't make it that way.